Here we are trying to discuss the formation of a Pn junction. A Pn junction cannot be formed by combining or simply joining separately formed P-type material and N-type material. This is because the two separate regions, when you try to join, there will be a discontinuity at the junction. This discontinuity can lead to imperfect conduction across the junction. The materials are already semiconductors, their conductivity is very low. If there is a discontinuity at the junction, even in the micrometer level, that can affect the conductivity. That's the reason why a Pn junction cannot be formed by combining separately formed P-type and N-type materials. The problem can be solved by taking a single silicon crystal and doping one side with group 15, so that side acts as N-type, and the nearby side with group 13, it acts as P-type. So there is no discontinuity, it's already there is a crystal structure of silicon. In that we are doping one side as group 13, nearby side as group 15. The process simply looks like this. Here we are doping with group 13 atoms. Each group 13 atom demand 4 electrons for bond formation in the silicon crystal structure, which is tetravalent, group 14, but it only has 1 electron less, group 13. It accepts 1 electron from silicon, that creates a hole in silicon and the atom becomes a negative. This process of formation of P-type and N-type is mentioned separately in another video. So similar to that, the negative ions and holes are formed according to the number of dopants added. So each negative ion, the group 13 atom, create one hole. Other than this, there are few free electrons and holes formed due to thermal excitation. The electrons from valence band move to conduction band of silicon, creating a free electron, leaving a vacancy called hole. So there are 2 free electrons and holes shown due to thermal excitation. The rest all are due to group 13 atoms absorbing 1 electron from silicon. The holes are the majority charge carriers, highly concentrated compared to the free electrons in the P region. In N region, we are doping with group 15. Group 15 atoms have 5 valence electrons, 4 only needed for bond formation in the crystal structure of silicon. The 5th electron leaves the atom, becoming a free electron by absorbing thermal energy, thermal excitation. That makes the group 15 atom a positive ion. So all these are group 15 atoms which donate 1 electron free by thermal excitation. And there are few free electrons and holes due to thermal excitation of electrons from valence band of silicon to conduction band of silicon. This process happens always in every semiconductor if temperature is greater than 0 Kelvin. So here there are large number of free electrons due to the doping with group 15 and very few holes due to thermal excitation. The free electrons are the majority charge carriers compared to holes. The hole is represented by the vacant circle, free electron by filled circle. The negative with a circle represent the negative ion, which is immobile. It's acceptor ion because accepting 1 electron to become negative. And the circle with plus represent immobile positive donor ion. Positive because lose 1 electron, donate 1 electron is called donor. Now there are 2 important processes during the formation of a Pn junction. One is called diffusion and the other one is drift. When you discuss diffusion or write regarding diffusion, make sure it's a process happening from higher concentration to lower concentration. So the background should be ready, mentioning there's a higher concentration on one side and lower concentration on the other side. Similarly, when drift is explained, drift is due to movement of charge carriers because of the electric field. So make sure there's an electric field when you're trying to explain the drift. Here, the higher concentration of free electrons, maybe they have a mutual repulsion, or normally higher to lower concentration moment with a diffusion movement. Electrons start moving from N to P. So these electrons will combine with the hole. So the electron combining with a hole is actually absence of one valence electron. When a free electron comes and fill the hole, the free electron will disappear and the hole also will disappear. Like a person moving, he comes and sit on a vacant chair. We don't see the person free moving, we don't see the chair to be vacant still. So each free electron movement from N region to P region due to the concentration difference will lead to recombination of free electrons with holes. Now the excitation of a free electron from conduction band to valence band will fill the hole, and this process release energy. Normally when an electron is jumping from valence band to conduction band, it absorbs energy. That energy only helps the electron to jump. That time a hole is formed here and the electrons become free. So this process absorbs energy. The de-excitation will release energy. In silicon or germanium, the energy gap is in the order of silicon 1.1 electron volt and germanium 0.772 electron volt. 0.72 electron volt, that range. These both are in infrared region. So the free electron hole recombination releases energy, photons in the order of infrared region. Since these are infrared region, these rays are not visible to human eye, but they are detected as heat. The junction becomes hot. So every free electron combining with a hole near the junction lead to formation of this infrared radiation. Now you can see near the junction, the P region has a layer of negative ions, the N region has a layer of positive ions. This creates an electric field called junction field. The direction of electric field is from plus to minus, meaning N region to P region. This electric field is important when you explain the drift. And the movement from higher concentration to lower concentration, that was diffusion. The junction field is creating the drift. That's why I mentioned in the beginning, when you explain diffusion, give importance for the concentration difference. When you're trying to explain drift, give importance for the electric field. Now the diffusion is due to higher concentration moving towards lower concentration. So free electrons from N region go to P region and holes from P region go to N region. That's called diffusion. And the current produced due to this diffusion is called diffusion current. Direction of current is opposite to the movement of free electrons, negative charges. Electrons go from N to P, so diffusion current is from P to N. Or current is in the movement of positive charges. Holes positive charge move from P to N. So same direction of diffusion current is from P region to N. Now when you start explaining drift, the combination leaves a layer of positive ion on N region and negative ion on P region. This creates an electric field called junction field directed from N region to P region, positive to negative. This electric field can accelerate holes from N region to P region. This negative can attract holes from N region to P region, and this positive layer can attract electrons from P region to N region. So due to the electric field, the charge carriers get accelerated across the junction. Electrons move towards the N side from P side, and holes move towards P region from N side. That's called drift. So these are the two important processes during the formation of Pn junction. This is what we discussed just now. The holes due to higher concentration move towards lower concentration region, N region, and the free electrons from N region move towards the P region. That's called diffusion. And here you can see layer of positive ions on the N region, negative ions on the P region, and this recombination releases infrared radiations. The same process what we discussed. Now the recombination leads to formation of negative layer of ions on P side and positive layer on ions on N side. This creates a potential difference. Since this potential difference acts as a barrier against further recombination, meaning these negative ions repel the electrons from entering N side. Already some of them entered. The rest of the electrons are stopped from entering because of the negative ions, and the holes positively charged get repelled by the positive ions, so they also stop from entering into the N region. So this potential difference formed due to diffusion, since acts as a barrier fencing against further free electron hole recombination, that's called potential barrier. It's a potential which acts as a barrier against further free electron hole recombination. For silicon diode, generally the value is 0.7 volt, and germanium diode the value is 0.2 volt as the potential barrier for normal dose. Now near the junction there are no free electrons or holes. There are no mobile charge carriers. The electrons and holes are the moving charge carriers. What is present here is only immobile negative acceptor ion and immobile positive donor ion. Since there are no free electrons and holes, they are lost, depleted. Depleted means lost due to recombination. That particular region where there are no free electrons and holes, known as the depletion region. The width of the depletion region is normally in the order of micrometers. Now, this is the important process during the formation of Pn junction. The two main processes are diffusion and drift, that is associated with formation of potential barrier and depletion. These formations are normally asked for the exams. Here is another diagram. This shows the variation of potential barrier across the junction. So this P side is at lower potential negative. The N side is at higher potential positive. The central region will be zero potential because negative and positive potential add up and cancel off. So going to the left side, the potential decreases, and going to the right side, potential increases. The center will be at zero potential. So this diagram shows the variation of barrier potential. Since the potential difference is only important, there is no zero string. Actually, there will be a zero line here, the central line. So this will be negative and this will be positive, and this part will be zero. but normally the diagram is drawn without the axis.